Hello and welcome everyone. Welcome to AIOps. Forward-looking statements. I was gonna throw the lawyers under the bus. So obviously they discovered the software industry. So what this statement basically means is I can stand up here all day long, make all kind of claims, all kind of statements about future releases, and we may or may not deliver on them. But the reality is that what we're going to talk about today is all going to be based on released product. So all the stuff that you guys are going to see here today is all in the released versions of the products for at least the last 12 to 18 months. So let me quickly introduce your speakers today. So my partner in crime today is Mr. Pierre Brunel. Very late addition to the team because my initial co-presenter had to drop out. He's going to be silent but deadly. And my name is Martin Weiser. So what we're going to do, what we're going to cover today is we're going to talk about AIOps. So here's the rough agenda. We're going to start out by looking at ITSI and the machine learning components, the turnkey machine learning components in ITSI. Then from there, we'll go into what is AIOps and what are some of the AIOps use cases. Then we'll do a quick deep dive into some of the machine learning concepts, and we're gonna present a use case for AIOps for a new operations center. And at the very end, we're gonna build a self-learning recommendation engine. So we're gonna switch over to Pierre's laptop and build this. Now, a recommendation engine may have different meanings to different folks. So if you guys browse on Amazon, if you guys browse on Netflix, and you see a movie, it says, well, you like this movie, maybe you like this. You like a different movie. So that's not the kind of recommendation engine we're talking about. So we're not saying, hey, you like to work on database events, maybe you also want to expand and work some network events. The recommendation engine we are gonna do is, very often in operation centers, we have a lot of junior staff, and we want to make sure we give them recommendations, kind of like a knowledge base, kind of like a guided direction on what they should actually do and what they should actually perform on those type of events. So let's take a look at the machine learning in ITSI. So 1876, 2015 is when we released ITSI. So 4 years ago, 5 confs ago. And back then, our machine learning capabilities were all in the realm of adaptive thresholds and anomaly detection. So adaptive thresholds is basically a statistical method that looks at what should the threshold be set at any point in time. So think about a key performance indicator like the number of logons to your environment. That number is very different on a Monday morning than it is on a Friday afternoon. So what you want to do is you want to have different thresholds depending on the day of the week, depending on the time of the day. So in our first release of ITSI, adaptive thresholds was a key feature. Then we released anomaly detection at the same time. So in our first release, this was all done with a publicly available mechanism called hold winters. And since that time, what we did is we basically wrote our own anomaly detection mechanism. So what anomaly detection does is it looks at a time series, think of it 5, 5, 5, 5.8, 12, and tells you that this 12th data point looks very different than the previous data points. So it lets you know that it doesn't really know much about the anomaly, it just tells you that this is a complete outlier. Now, around version 3 of ITSI, we released what's called cohesive anomaly detection. So rather than looking at KPIs in general, we could now look at different entities and figure out if they have an anomaly. So for example, if I have 5 web servers and 4 of them are processing around 200, 300 requests a second, and one of them is processing 800 requests a second, cohesive anomaly detection tells me that, well, this one web server may have either had a bad code push or may have a load balancer that's sending too much traffic to it. But bottom line is that the cohesive anomaly detection figures out anomalies across the entities in ITSI. Now, in version 4 of ITSI, we also released predictive analytics. And predictive analytics is kind of a cool feature, but not a lot of customers are using it yet because many of our customers are still struggling with what to do if nothing is broken yet. So every customer is really good at fixing problems once stuff breaks, but if somebody tells them in their ear, hey, the way you're running this, it's gonna blow up in 5 minutes, nobody really knows what to do as far as the processes go. But at least the capability exists in ITSI. And we have clustered events. So when you get a bunch of individual infrastructure alerts, at that point in time, we cluster those events through machine learning together. Now, those are all the out-of-the-box capabilities for ITSI as far as machine learning goes. But at any point in time, we had the capability of integrating the Machine Learning Toolkit into ITSI. And the Machine Learning Toolkit is a free Splunk application, basically available on Splunk base, that allows us to extend the machine learning, the out-of-the-box, the turnkey machine learning that ships with ITSI. So let's take a quick journey into AIOps. So here's the Gartner slide as they defined, as they coined the term about 2017, a couple years ago. And what immediately happened is you had all the different vendors see where they fit in this space. So you have some vendors that basically just look at monitoring, and for them AIOps is all around how can a cluster events better together. You have the service desk vendors like BMC Remedy, ServiceNow, Sharewell. For them, it's all around the engagement model, taking action on that data, but it's very service-centric, service desk-centric. Then you have the automation tools, and they haven't really done too much marketing in this AIOps space. But to me, AIOps is really the intersection of big data and machine learning with any of those data sources. So I don't want to disqualify any data source. I don't want to say one data source is more important than another one. But bottom line is that all those data sources produce a wealth of information. And what we want to do is we want to take advantage of that data by putting machine learning on top of that. Now, why do I think that Splunk is great at this? Well, there's a couple of different theories, right? I could stand here and say we have the smartest machine learning engineers, or we have the most complex neural network. But the reality is, if you go from the Splunk headquarters a couple blocks in San Francisco to a different location, you'll find some machine learning startup that probably has a similar capacity as far as their data scientists goes, as far as their engineers go. So the reason why I think Splunk is great at this is because we have a ton of data. All the data that you have in Splunk can be used to be converted into features, into machine learning features. So the more features you have, the better off you are from a machine learning perspective. So something that Splunk very often has is high volume, low value data. So those data elements may just be the amplifier you need in order to find the signal in the noise. So a JMX memory utilization in combination with 3 or 4 other indicators may just be the prediction that you need in order to do that. And yes, APM data, super valuable. Service management data, super valuable. Infrastructure data, virtualization data, cloud data, super valuable. But there isn't a single data source out there that is significantly better than another one for machine learning. So again, the reason why I think Splunk will have a huge part of this AIOps revolution is because we have so many diverse data sources and we have so much data that basically where the signal gets amplified based on the various data components. Now, when you look at AIOps, all the AIOps use cases basically try to do very similar things. They try to eliminate tedious tasks. They try to reduce the noise and figure the signal out very quickly, very efficiently. They try to get you to the root cause quicker, to shut down or to reduce the time to investigate, to reduce the time between errors. So those are all the typical drivers for AIOps type use cases. What we are going to focus on today is we are going to take event correlation and analysis, and we're going to try to eliminate a lot of the tedious tasks. So we're going to build a model on top of an ITSI implementation, and we're going to productionize that model and basically have the operations center perform some actions on that data and then feed that into the model so we can predict what kind of action should be done on certain type of events. Now, before we do that, let's take a quick look at some of the major machine learning concepts. So there's one concept that basically tells you if you have data and you don't know the outcome of that data, it's going to be unsupervised machine learning. So the data that you have is not necessarily labeled, and this is what most of the data in Splunk looks like. So if you think of any kind of CPU utilization, you don't know if the CPU utilization was 95 because the database server was down and there were some timeouts, or just because the user traffic was high on the front end side and basically pushed that server to that kind of CPU utilization. So because we don't know what the circumstances were, a lot of the data, as I mentioned, in Splunk is unsupervised. My personal preference is to work on supervised machine learning algorithms, but because we have so many unsupervised ones, I wanted to tell you guys about some pitfalls we have encountered in the field. So if you think of unsupervised algorithms, or if you think of a basic use case, like I want to know before anybody knows if my server is running out of resources, right? Pretty basic use case. So we had a very large healthcare provider, about 60 million subscribers. They wanted to basically monitor their open enrollment infrastructure. So with the open enrollment infrastructure, you're basically highly over-provisioned for the most part of the year, but then whenever the fall comes and all the different companies sign up for the open enrollment, at that point in time, you want to make sure that you have enough resources available to basically perform your activities to let the users, the beneficiaries, do this open enrollment. Well, this particular healthcare provider was going to do unsupervised machine learning on CPU data. So think of the time series that looks like this, 5, 5, 7, 5, 10. All of a sudden, the CPU utilization jumps to 10 because some antivirus may have kicked in or who knows what, some I/O buffer was full and had to be written to disk. So what happened was we created an anomaly, we let the administrator know, and we did this many thousand times. So the administrators were very frustrated with us and said, hey, this thing has 90% more to go. Why do you notify me just because it jumped from 5 to 10? Now, again, the algorithm does not know what kind of data it is working on. So think about a different scenario. Think about the unemployment rate. If that goes from 5 to 5.5 to 4.5 to 5 and all of a sudden jumps to 10, everybody would be up in arms and say, hey, this is a huge anomaly. Obviously, the algorithm doesn't know, does it perform against the CPU utilization, CPU percentage utilization, or does it perform against the unemployment number? So we had another a payment card provider actually process or have a KPI, a key performance indicator, that would track the number of Apple payments per minute. And it was a fairly small payment card provider, but the numbers were in very similar spaces, like 5, 7, 10. Now that number isn't even bound by 100, so if you feed that data into an unsupervised algorithm, like they could literally have 500 or 1,000 Apple Pay payments going through their credit cards. If you feed that through an unsupervised algorithm, you'll always be at a disadvantage because the algorithm basically does not know anything about the data. Now let's switch over to supervised machine learning. The problem with supervised machine learning is that you have to label the data. This is a lot of effort. You have to say, is this a good outcome? Is this a bad outcome? Based on the data you have feeding in. Now, one area that many of you guys have deployed where this data gets labeled kind of for free, I don't want to say for free, but where the data gets labeled, is in the operations center space. So unfortunately, there were no pictures of network events, of infrastructure events, so I took cats, but they kind of follow the same standard. So you have the big fluffy cat that's more like an APM thing, super telemetry rich. You have the skinny cat that's like a mainframe alert, like a bench job, whatever, with a severity code, and that's all you get, but it's super serious. So you get the events, and you have your operations center staff label the data. So they are saying, okay, for this storage event, we need to expand the table space, for example, for this database. For this firewall event, we need to perform a compliance check. So they perform a lot of human work that you can then feed into the machine learning pipeline and basically perform custom machine learning on that, so you can make it easier if the next fluffy cat comes in to say, okay, in those kind of scenarios, this is what we typically do. Now, operation centers have their fair share of challenges. So they have very high turnover. Like, not everybody wants to work 24/7 or wants to work at night. And it's a pretty high-stress job. So what we want to do is we want to assist the operation center staff as much as possible. Now, what we are talking about here, doing this all through machine learning, isn't anything new. Like, we had customers, like literally 25 years ago, building static rules that said, if you see this event on this server, perform this action. The problem with IT over the last 25 years is it grew. 25 years ago, you knew the name of the server. You knew what application was running on that server. They were all your pets. Nowadays, with dynamic resource scheduling, with elastic, everything, with containers, stuff spins up, goes down left and right. So you need to come up with something that takes advantage of dynamic rules, meaning something that ran on one server today may be running on a completely different server a couple days from now. So the rules, the static rule approach does no longer work. So you have to come up, and this is where machine learning is great, you have to come up with a way where you keep this current, where you train the system, and then basically build that into a rules logic that can be followed. And then, the last point is, people don't always necessarily follow instructions. So you tell them that every time you have a storage event, go ahead and log a ServiceNow ticket, for example. Like, they'll do it 95-ish, 90-80% of the time, but sometimes ServiceNow may be down, or it times out, or the guy has some other fire he needs to attend. So it's not a complete, clean data set. Now, like I said at the beginning, my favorite Splunker for the last week, because he jumped in on really, really late notice, is Mr. Pierre over here. So Pierre, let's do a quick role play. So Pierre is working for a company called Bazookatron. And Bazookatron implemented AIOps, or implemented ITSI, about a month ago. So what happens is, the system went live, they collected some data. All of a sudden, Pierre's boss shows up and says, hey Pierre, what's our AIOps strategy? Comes out of some executive meeting, has no idea really where to begin. Now, the second time he asks Pierre the question, he's like, hey Pierre, what's your AIOps strategy, right? So he puts the burden on Pierre. Now, Pierre is not a dummy, right? Like, he understands his data, so he understands exactly what kind of stuff goes on in the environment and what is very repetitive. What are some of the tasks that his operation center struggles with? So Pierre immediately jumps up and says, well, we got 3 use cases for our AIOps strategy. The first one, remember that server called app1057 that runs the custom human resource software that we got somehow in our environment from the most recent acquisition? That one has a memory leak, and the vendor says it's going to take them 4 months to fix it. So literally every other day, we have somebody in our operations staff having to kill the process, having to kill the memory on this thing just to keep this thing alive. So wouldn't it be great if we could help our junior analysts to be more comfortable whenever they run this process kill command? Now, at the same time, we have a lot of firewall alerts. Every time we get a firewall alert, nobody's always sure. We need to run this compliance script to make sure nobody monkeyed around with the firewall rules. So why don't we try to automate this as well? And then for any kind of storage issues, we just went live with ServiceNow. We have this standard change out there. Why don't we save some time for our analysts, basically submit a standard change anytime we get an alert that basically says anything along the lines of storage. So this is what Pierre's proposal is for AIOps. Pretty reasonable use case, 3 very basic recovery actions. So firewall issue, run compliance script. If it happened on this one server, perform this special kill command. And if it is a storage issue, basically go ahead and do your ticketing. Now, Pierre's gonna look at the data, and as he looks at the data, he figures out that, well, the data looks good, but it's not perfect. So again, at any point in time, users may have accidentally performed the wrong action or may not have been fully compliant with the rules that they were given in the operations center. So those are all rules that they are doing manually today. But as you guys can see, I mean, those are very realistic numbers. The hit rate, the action rate is north of 95%, and this is something that you guys should expect if you implement something along those lines as well in your environment. So the question is, can we assist the operations center, and more importantly, how are we going to do that? Well, we're going to use the Machine Learning Toolkit in order to do that, and we're going to use two very specific algorithms. One is called TF-IDF, Text Frequency Inverse Document Frequency. And what this algorithm does is it takes a text string, like a description that says SNMP trap, like a warm start, a cold start trap, or like node XYZ, is at capacity for disk space. It takes this and converts it into a numeric representation. So we can actually do some math on it. So it's a very powerful algorithm. But the problem is it adds literally hundreds, if not thousands, of fields to your Splunk search results. So it looks at all the different permutations of all the different messages that you may receive in your operations center and basically puts a field for each and every word onto your Splunk results. Now, this wouldn't be the worst if you're running on a box that has like hundreds of cores and terabytes of memory. But the problem is very often we do those projects in very limited environments. So the second algorithm that we're going to use is called PCA, Principal Component Analysis, or in our case, kernel PCA. And what this one does is it looks at all of those different permutations that are already in numeric format, and it converts it down to a much, much smaller subset of features that we can then feed into our machine learning. So the benefit with that is we can build models without having to run on supercomputers. So at this point in time, what we're going to do is we're actually going to show what this model looks like and how we're going to perform this action. So we're going to toggle over, and the first thing we're going to show is, well, what does ITSI for event analytics actually look like? So Pierre's going to click on one of those alerts, and this is basically what it looks like. So we see there's a van issue. It's in somewhere in Minneapolis, or it's like a MPLS one in LAX on node 137. We see some additional data, like what node did it happen on, what's the vendor potentially for this particular circuit or for this particular wide area network component. But bottom line is that those are events that come in to ITSI left and right, and those are the events that your operations center handles. So the way they handle them manually is they would basically just look at that event and perform an action on it. So perform some basic recovery steps against that event. Something like, hey, let's try to bring this up. If it doesn't work, let's cut a ticket. So the next thing we're going to do is we're going to look at a search, and that search is specific to ITSI, but it doesn't have to be. So if you have your data, your event analytics platform somewhere else, like in Netcool, in any of our competitors' products, if you have the data in Splunk, you can still follow along with a very similar approach. So what this search does is it basically looks at the text on the one hand, it looks at the node ID where this particular event happened on the other hand, and then it tells you what the action is that, in this case, the operations center has performed. So on this first page, it looks like all of them are no actions, but let's browse through maybe a couple more pages. So we see maybe a ServiceNow event, or ideally a database event, or a compliance event. Or maybe we stick with the no action until we actually, find something else. So those are all, probably good examples of 10,000s of events that don't have any kind of alerts on them. Maybe sort by the my result. Okay, maybe let's go back to the search. change the time frame. So I think change it to 10:10 on the right-hand side. Sorry about that little snafu, but that is still a very powerful mechanism to basically see this. So in this case, we see there is an event. It happened on this server called app1057. So that's our human resources server that's running out of memory. And in this case, it triggered the recovery script. So we see that, okay, this is the representation of the machine learning model before we actually convert anything into numbers. So the question that we are asking is, can we predict the right-hand side, the column on the very right called my result, based on the combination of the node ID and based on the combination and the description of the alert. And the alerts are just going to be some very, very dynamic events that basically show up in your infrastructure. So that is the use case. So in order to do that, we'll go into the Machine Learning Toolkit. In the Machine Learning Toolkit, we basically perform the exact same search. So we bring this exact same data set into the Machine Learning Toolkit. And what's great about the Machine Learning Toolkit is it's a great playground for us to really work with that data. It's also a playground where you can very easily get lost and spend 8 hours without really producing a lot of results, but that's a different story. So what we are doing here is we are basically saying, okay, the first thing we're going to do is run this text frequency identification on this node ID. And in our sample, in our 10,000 network events, in our 10,000 application events, whatever they were, we had about 1,000, what's the number, 1,336 different nodes that reported a problem. So at no point in time do we limit this to just the one node where we know it's app1057. So there are like 1,300 different permutations for this. Now once we've done this, Splunk internally added 1,337 or whatever the number was, new fields to this search result. So basically the memory requirements ballooned at that point in time. But we are not done with this. So the next thing we need to do is do the exact same step on the description. So the description can have wide area network events, firewall events. You guys saw all the different permutations. So there's another 1,900 additional fields, additional columns that gets added to this search result. So at this point in time, we are probably close to 4,000 different fields in the result set. So very, very large memory consumption. So the next thing we need to do in order to really take advantage of that model and really make it something we can use in production, because if we have 4,000 fields, like the memory requirements as well as the processing requirements would be way too much. The next thing we need to do is we need to reduce the number of features, the number of components in our model, and that is done with this kernel PCA, so the principal component analysis. Now in this kernel PCA, there's a couple of different tuning parameters, but the most important thing that you care about is the number of components. And the reason why we picked 7 was because the result was more or was better than when we picked 5. And 5 was better than when we picked 3. Obviously, there's a little bit of a trade-off. The more columns you keep in your result set, the higher the memory requirements are going to be. But at the same time, the more precise your prediction is going to be on that result set. So 7, 5 are really good numbers to work with. So now we are formulating the question, and we are basically saying, based on the algorithm called random forest, based on this classifier, based on the 7 fields that represent different terms in the node ID and different terms in the description, can we predict the my result? Can we predict the action that the operations center should take? So as Pierre is scrolling down, one of the really cool things in the Machine Learning Toolkit is it gives you an immediate indication of, is this a good model or not? So you have things like accuracy scores. You have things like, for example, the precision of that model. And most importantly, you have what's called a confusion matrix. So you see, when did we predict it should create a ServiceNow ticket? and when did it actually create the ServiceNow ticket. So we see that there's a 95% match. So this is a pretty good model. When did it predict to take no action, and when did it actually, when it was it supposed to actually take no action? Again, 97%. So those are really good numbers in our model. So obviously you tweak the parameters in the machine learning toolkit as much as you want until you come up with a model that fits your requirements. So anything from my perspective that's north of a 90% or a 0.9 accuracy, 0.9 precision is definitely something that I would go into production with, but that's my personal opinion. Obviously, every customer will have different constraints as you guys possibly use machine learning for that. But those are really good model numbers. Keep in mind that even the data that we inputted into the model wasn't that clean to begin with. Like some of them had 96, one of them had 98% accuracy. So based on that input data being a little bit dirty, those numbers are really spectacular. So if we are happy with this model, at that point in time, what Pierre is going to do is he's basically going to look at that model and he's going to publish that model into ITSI. So he hits the publish button on the machine learning toolkit, and at that point in time, he can say, take this model and shoot it over, make it available to the ITSI application. So now that model basically, got created. It is now available in ITSI. So now let's take a look what this model actually looks like in ITSI by taking a look at the actual correlation search. So before we do that, let's take a look at the initial correlation search. So the initial correlation search was basically just reading data from one index. So as the data was getting into this index called alert data, all it was doing was basically taking advantage of that data, putting the description field into the notable event title, putting the severity or the priority into the severity column, and that's pretty much it. So now let's take a look at what the new search will look like, where we take advantage of that model in the machine learning toolkit. So the base search, the base component looks exactly the same. So look at this data set, bring in the data, but then apply the model. So the first model is going to be the TF-IDF on the node ID. The second model is going to be the TF-IDF on the description. Then perform this principal component analysis, and then apply the random forest mechanism. And because we added literally thousands of fields to this, which potentially makes ITSI barf, at that point in time, let's remove all those fields that we don't need so we can free up the memory. So go ahead and take out the TF-IDF fields and take out the PC, the principal component fields, but that's basically the difference in the search. So once we enable this search and the data comes in, at that point in time, what we should see is we should see new events come in, and those new events will have a predicted my result. So Pierre is clicking on this firewall issue here, and the predicted my result, the hint for the analyst is, hey, in those kind of use cases, you should trigger the compliance script. So it's kind of like a knowledge article, like a hint that gives them at least something that they can do to manually perform that action to have a second opinion. So really great use case for some of the junior analysts. So rather than them looking at some operating instructions, they get the hint directly from the tool. And more importantly, that model gets updated as things change. So as your operation center performs different activities against different nodes, that's all incorporated into that model. So at any point in time, can that model be refreshed? Can that model be redeployed? So in this case, we see, okay, the predicted my result is to trigger the compliance script. So we are good. We are done with our work. Now Pierre's boss comes back and says, well, can we fully automate this? Can we take this, and for those type of activities, can we actually go ahead and automatically trigger the compliance script so that our junior analysts don't even have to do that part? And the answer is absolutely yes. So within ITSI, we have what's called notable event aggregation policies. And within the aggregation policies, what we can do is we can basically add a new rule in there, and that new rule says, if you see the following event, if the following event occurs, and that one says the predicted result matches anything compliance, then automatically trigger the compliance script. Now the difference between this and a static rule is, again, that this gets updated as your environment changes, as your infrastructure changes. So at that point in time, what we have is, we basically have a machine learning model deployed in ITSI. ITSI has an automated action taking advantage of that model, looking at the data, and performing the action automatically. So if you think about this kind of like a flywheel, you would start out with your low-hanging fruit items, with the stuff that is super common to basically get analysts' input on. You would make it semi-automated for the first release. You would automate it for the next release and have the next set of activities, the next set of servers, the next set of activities basically participate in the next iteration of that model. So with that, you can automate more and more, and your operations center still does the work. So they label the data for you, but then at the same time, all the low level activities are all basically taken care of automatically for you. So with that, let me jump back from the demo to my screen here and get to the right slide. So with that, we basically reviewed the AIOps use case. We implemented some very specific examples for operation centers. The reason why we picked this is because operation centers are super common across our entire customer base. So when I said, this is all based on released product for the last 12 years, for the last 12 months, I wasn't lying, but it took us a while to figure out data sets that are really common across our entire customer base. So it took a little bit of research on our end. Then we had to internally figure out, okay, based on that data set, how repeatable is this across different customers? And that's what we came up with. So we analyzed the data set, we explored different machine learning algorithms on top of that. We didn't really cover too much of the machine learning toolkit, but you guys saw the capabilities of that workbench. Then we very quickly operationalized that model. This is orders of magnitudes quicker than you can do in many programming languages even. So we operationalized that model, fed it back into ITSI, and we ended up with a full-blown recommendation engine. So with that, let me stop here for a second. We got about 7 minutes left and open this up for questions. Okay, first question. So the question was, obviously your environment changes and therefore that model needs to change. So does the machine learning toolkit have a built-in retrain or a scheduling mechanism for retraining? And the answer is yes. Okay? Okay, hold that thought. Let's meet outside in 5 minutes. Any other questions?
After you train the model to publish it to the ITSI app, okay, instead of, let's say like in my environment, I don't have ITSI app, so can I publish to the such app and schedule the event?
Absolutely. So the question was, What if you don't have ITSI, right? Like I made this comment earlier, like if you have Netcool or, insert your legacy manager tool here, can you still do this? And the answer is absolutely yes. So in that case, obviously you wouldn't schedule it into ITSI. You would split your data feed to go into Netcool, go into Splunk. In Splunk, it would predict what the output is, and what you would do is you would build a basic dashboard that links your Netcool event to that event in Splunk, so you would use the event ID as, or some unique identifier to basically do that, and then just have the analyst click on it, pop up a screen and says, well, Splunk says you should run the compliance script, and it's still helpful for some junior analysts. Okay? Any other questions? Yep. So the question was, do we have libraries for models for the most common type of scenarios? And the question is, what's the most common type of scenarios? So we definitely have what I would consider the standard set of libraries, like predicting a time series, figuring out different kinds of outliers, making a categorical prediction. So there's about 9-ish or so that are published with really, really rich example use cases and example data with the Machine Learning Toolkit, so you can get familiar with that, so that's the good news. And then the second part of the good news is, like all the algorithms themselves are, exist for a long time already. Like principal component analysis isn't something that somebody invented in the last 10 years. Like random forest regress classifiers have been around for at least 10, 15 years. So all the libraries that we use basically are built on top of what's called scikit-learn, which is a Python library, but it should give you the exact same result as if you were running this thing with SAS, as we heard earlier, or with R, which is a different language for statistical analysis. So all the algorithms are very robust, have been around for a really, really long time, and we expose, like I said, a bunch of them with really rich use cases to get you started. Now, there may be use cases out there, like predict tomorrow's close of the stock market. May not be that easy with the algorithms out there. So there may be some algorithms that have yet to be exposed, or more importantly, that we can leverage within the Machine Learning Toolkit. So the scikit-learn libraries, I think, are in the neighborhood of 100-ish, 150-ish libraries. And like I said, a subset of them, the most common ones, are definitely exposed for us.
And there's an API, so you can, and I'll try to talk loud so everyone can hear. There's an whole API associated with Machine Learning Toolkit. So if there are algorithms that aren't part of the Machine Learning Toolkit, there are the capabilities to embed them so that they can be used within the Machine Learning Toolkit. In fact, there's a GitHub account where I have all these algorithms that have been imported using that API. So,
depends on the size of your environment, right? So, it takes one, like the apply function, remember the correlation search, right? And then we did apply this, apply this, apply this. Basically consumes one core until it's fully applied. Now, if you have many other cores, right, but also a lot of other search load, think of this kind of like a real-time search. So you definitely want to have a little bit of headroom in your system before you actually do anything like crazy. But that's not just the Machine Learning Toolkit, that's also ITSI. Like even within ITSI, just installing ITSI adds a little bit of load on top of that. So you want to make sure you go through a basic sizing exercise before you go nuts.
and if I could add, separate to the Machine Learning Toolkit app, there's also an ML performance app that has within it a lot of the results for some of the scale testing. So the type of algorithm for the fit, for the apply, how many features, how many rows of data, and that'll give you a sense of, whether or not what you're looking to do, you should be, careful around.
Does that provide that for execution, model apply, model and training?
Yeah. So for both. Yeah, so for both the fit and the apply, It'll give the, the amount of memory and the CPU seconds and a couple other metrics.
Can you say that name one more time?
ML Performance App.
Cool, one last question before we get kicked off the stage. Sweet, thank you very much.